Hello students, I am Dr. Rajiv Sapre and this is lecture number 44 about the topology of metric spaces. And in this lecture I will start discussing a new chapter, sequences, which will be further, we will go for complete metric spaces and all that. But to study complete metric spaces properly, we should have a thorough understanding of sequences. Now sequences already you have studied in previous years in FY, SY, BSc. But now we are going to study sequences with respect to metric space. So the issue is this, that you have a metric space x comma d, correct? X comma d is a metric space. Now all of you know what is metric space. I am not going to repeat that. Only I will tell the definition. Metric space is what? It is actually this X is the underlying set, and you have a function d from x cross x to set of real numbers, and this function satisfies certain properties. Those properties we know. We know that we have these properties. dxy is greater than or equal to 0 for all x and y belonging to x. Okay, then what? dxy is equal to 0 if and only if x is equal to y. This is the second property. Then you have dxy is same as dyx. This is called symmetric property, and this is true for all x and y belonging to x. And the next property, you know, it is a very famous triangle inequality. What it tells you, dxy is less than or equal to dxz plus dzy. This is triangle inequality, and this is true for all xyz belonging to x. When these four properties are satisfied by this function, which is from the Cartesian product of x with itself, which is the domain of that function, and R is the codomain. That means it will be a non-negative real number. Distance cannot be negative, as you always know. So this type of function, whenever it satisfies all these four properties, then you call this d as a metric, and x comma d is a metric space. This is all you know, just I am repeating it. What is sequence now? Sequences of real numbers we have studied, right? And sequences of real numbers went what? It is a function actually. Every sequence, suppose I talk about the sequence of real numbers. Sequence of real numbers. It can be sequence of any set. Here I am underlying set, I am taking R. Sequence of real R. R means this R, real number set. What is it? It is a function from the set of natural numbers to R. Right? Any function which is from the whose domain is set of natural numbers is a sequence. What is the codomain here? R. So I will say this is a sequence in R. Right? If this it is a function from n to n, it will be sequence in x. Sequence in n. If it is a sequence, if it is a function from, say, f is function from n to q, where q is set of rational numbers, then you will call it as a sequence of rational numbers. So what is codomain? That is important. If codomain is R, it is a sequence of real numbers. So now, as we are going to define a sequence in case of metric space x, what we will do? We will take a function f from n to x, right? So sequence, with what we can define, sequence, sequence, okay? Sequence on metric space x comma d is a function f from set of natural numbers to x. This is the sequence. Now what you always know is the set of natural numbers is this. No, set of natural numbers is what? It is, all of you know, it starts with 1, 2, 3 and so on. It goes up to infinity. Natural number set is not finite. All of you definitely know that. So whenever I operate the sequence, operate the function on the domain, I will get first term of that sequence f of 1. this will be element of x, because this is a function from n to x, right? So f of 1 will be element in the set capital X, right? Then you will have f of 2, then you will have f of 3, then you will have f of 4, this will be f of 4, and so on, because these are all natural numbers on which I am operating the function. So this is unending, infinitely many functional values you will get, right? These are called terms of that sequence. F1 is the term of the sequence. So instead of writing all these things, what you can do, f of 1 you can take as, say, x1, f of 2 you can take x2, f of 3 you can take x3, f of 4 you can take x4, etc. f of n you can take xn, and so on, right? So what we will do, you will say that in triangular bracket xn is a sequence in capital X. xn is sequence in capital X. What this means? This is a function. हे जे xn आपण इथे लिहिलेलं आहे, these are the terms of the sequence. Whenever I operate the function on the set of natural numbers, you know, first natural number is 1. So I will get f of 1, you denote it by x1, f of 2 you denote by x2, f of 3 you denote by x3, and so on. F of n you denote by xn, and so on. It's not ending here. Set of natural numbers does not end at n, it continues. But this is the general term, and general term of the sequence is enclosed in triangular bracket. Some authors use circular bracket. Anything is okay. That notation does not means whenever you change notation, results do not differ. Same results you will get, but you should be conversant with some proper symbolic representation. So I will use in my lectures triangular bracket. I will use for the sequence. So xn is sequence in X. Once you say, it means it is a function from natural number set to X. So I will operate the function on natural number set. That means I will operate the function on 1, 2, 3, etc. The outcomes of that function, that means functional values, will be from X, which is the metric space. X comma d is the metric space that is assumed. So here I will say, let x comma d be metric space, and then f, which is a function from n to x, is a sequence on metric space x comma d. I hope you understand what is sequence. Some examples I will give, and then we will proceed further. Some examples. I will erase this now. Okay, this is not needed now. Okay, so suppose I take what? Say I take a real number set R comma D. You know, this is a metric space, usual metric. What do you mean by usual metric? You know, it is dxy. Definition of D will be mod of x minus y. Now this is the metric space, already we have proved. Now if I consider the sequence, if I consider say function f from the set of natural numbers to R, okay, and my function I will define as f of n is equal to 1 upon n, 1 upon n for all n belonging to capital N. This is my function, suppose. Now what happens here? You can see my terms of that sequence will be f of 1. F of 1 will be what? 1 upon 1. So 1 upon 1 means 1. Then 1 upon 2, because n when it is 2, it will be 1 by 2. Then when n is 3, it is 1 by 3. Then when n is 4, it is 1 by 4, and so on. So this will be the sequence, right? All these terms. So I will denote this sequence by this 1 upon n. What is done? General term is enclosed in triangular bracket. Here general term is 1 upon n. I will enclose it in triangular bracket. So I get a sequence. So 1 upon n is sequence in R. 1 upon n is sequence in R. And this terms of the sequence will be 1 upon 1, 1 by 2, 1 by 3, 1 by 4, and so on. So many examples we can give. So this is first example. Okay. Now another example, I will erase this now. You should be equipped with examples. Now second example that I will be giving you is say f is a function from the set of natural numbers to R. I am again going to give you a sequence in metric space R comma D. This is underlying metric space. So definition of that will be f of n is equal to say n squared. So now for all n belonging to capital N, this is the definition of that function. So what will be the terms of the sequence? First you are putting n is 1, so it is 1 square, then 2, so 2 square, then 3, so 3 square, and so on. Right? So this is the sequence: 1 square, 2 square, 3 square, and so on. General term you can say n squared, and so on. That means what? Means what we can say is, we can say are terms of the sequence. Right? Generally, not generally actually, this set that we are talking about, that means 1, 4, 9, then 16, and so on. General term will be n squared, and so on. This is called range set of the sequence. Range set of sequence. What do you mean by range set? These are the functional values. Set of functional values, we know it is called as a range of that function. But here this function is nothing but a sequence. So this is the range of that sequence. This is the range of this sequence 1 upon n. 1, 1 half, 1 by 3, 1 by 4. हा जो आपला set आहे, that is range of this sequence. This is range of this sequence, n squared. General term of that will be given by n squared. Another example we will take. Say f be the function from n to r. Again I am talking about sequence in usual metric space r comma d. So by definition of the sequence will be function, definition of the function will be f of n is equal to minus 1 raised to n. Okay. So now what is this? What will be the terms? What will be the range set of this sequence? It will be, first term will be minus 1 raised to 1. Sorry. I will erase this. It will be minus 1 raised to 1. Second term will be minus 1 squared. Third term will be minus 1 cube, and so on. Minus 1 raised to n will be the general term, and so on. So what I can say, it is minus 1 here, plus 1 here, minus 1 again, minus 1 cube is minus 1. Then next term will be minus 1 raised to 4, which is plus 1, and so on. General term will be minus 1 raised to n, and so on. So I have written 3 sequences here. First one was 1 upon n, definition of the sequence. General term of the sequence is 1 by n. Here the general term is n squared, right, where n is from capital N, natural number set. And here it is minus 1 raised to n. So these are the 3 different sequences that you can think of. Means there are many sequences that you can define on the set of natural numbers. Many functions can be defined which has codomain R. But we have, as an example, I have taken 3 sequences. First is 1 by n, second is n square, third is minus 1 raised to n. Another definition we will take, right, which will be, suppose f is a function from n to r, where f of x is equal to, or f of n is equal to 2 for all n belonging to capital N. What does it mean? Terms of the sequence will be, you operate f on any natural number, outcome is 2, right? So the terms of the sequence will be 2, 2, 2, and so on. Everywhere it will be 2. So if you call the range set of the sequence, range set of these sequences, when you consider first sequence 1 upon n, what is its range set? It is this 1, 1 half, 1 by 3, 1 by 4, and so on. Second sequence n square, range set will be 1 square, that means 1, 4, 9, 16, and so on, n squared, and so on. Then third is minus 1 raised to n. So range set will be minus 1 plus 1 minus 1 plus 1, etc. And finally it is fn is equal to 2 for all n, right? So all the terms of that sequence will be exactly equal to 2. So range set of this sequence, when you talk fourth, it will be just singleton 2. This will be doubleton set. So I will go to next slide and explain all this. See, first whenever you consider sequence 1 by n, then you considered sequence n squared, then you considered sequence -1 raised to n, and then you consider the sequence 2. It means what? Here the range set is this 1, 1 by 2, 1 by 3 and so on. 1 by n was the general term, and then so on. Here the range set was 1, then 4, then 9, then 16, then 25 and so on. Then it was this was -1 and +1, and this was just singleton 2. Why I am taking these 4 different examples? Here the range set is infinite, right? Range set is infinite. Actually you can prove that this is countably infinite. You can have 1-1 correspondence between the set of natural numbers to this set 1, 1/2, 1 by 3. By definition will be f of n is 1 upon n, which we can prove 1, 1 onto and all that. So this function or this sequence 1 upon n contains infinitely many terms. This also contains infinitely many terms, right? Because the definition of the function was f of n is equal to n square. So whenever you put different n's, you will get different squares. Here we are all considering positive natural numbers, positive integers actually. Set of natural numbers also can be considered as a set of positive integers. Here also, but here the range set of this sequence is just 2 elements. So what we can see here, that this particular set, so here I will talk about range set of that sequence. Range set here is infinite, but bounded. Why bounded? Because every element in this sequence is greater than 0, right? And less than or equal to 1. Greater than 0, less than or equal to 1. So what we can say, all the terms of sequence 1 upon n are such that 1 is greater than or equal to 1 upon n is greater than 0. So range set of sequence 1 by n is bounded. Range set of sequence 1 by n is bounded. Do you understand? So such a sequence is said to be bounded sequence. म्हणजेच तुम्हाला बाउंडेड सिक्वेन्सची डेफिनेशन काय, की ज्या सिक्वेन्सचा रेंज सेट हा बाउंडेड असेल तर तो सिक्वेन्स बाउंडेड. आता दुसरं म्हणजे काय म्हणणार? सो रेंज सेट ऑफ 1 अपॉन इज बाउंडेड, दॅट इज सिक्वेन्स 1 upon n is bounded. Obviously I am talking about sequence 1 upon n with respect to usual metric space R, D. बाउंडेड सिक्वेन्स आहे. का बाउंडेड सिक्वेन्स आहे? तर ह्याचा जो रेंज सेट आहे त्याला लोअर बाउंड आहे, अपर बाउंड आहे. व्हॉट इज लोअर बाउंड? 0. व्हॉट इज अपर बाउंड? 1. Lower bound is not there in that range set, but upper bound is there, 1 is there. So it is bounded sequence. What about second example you take? It is sequence n square. N square, that is second example. What you know, what are the terms in this? They are 1, 4, 9, 16 and so on. Now you can see here that these terms are increasing. 1, 4, 9, 16. This is an increasing sequence. There is no upper bound to this, but it has a lower bound. See, all the terms of this sequence are greater than or equal to 1. So if I take x belonging to this sequence n squared, okay, then what I can say, 1 is less than or equal to x. This is okay. Lower bound is there, but what about upper bound? There is no upper bound to this sequence because these terms are increasing. Okay, so what I can say, sequence n squared is not bounded. Sequence n square is not bounded. What about third sequence? It is obvious now. this is the sequence what? Minus 1 raised to n. When I consider range set of this sequence, it contains only two terms, 1 and minus 1. So this is a finite set. Range set of this sequence is finite, and you know every finite set is bounded, right? So as every finite set is bounded, every finite set is bounded, we can say minus 1 raised to n is bounded sequence. Bounded sequence. Okay, and finally this constant sequence you take, second, last example, only 2 is there. So what is the range set of this sequence? It is just singleton 2. On this side I am writing range set. This is range set. Here also this is range set. Here also this is range set of that sequence, etc. So just to consider, now this is finite set again. Singleton 2 means that set contains only one element. So as the number of elements in that set is finite, its cardinality of the set is finite, and as the set is finite, it is bounded. कुठलाही finite set हा bounded असतो. त्यामुळे काय झालं बघा, हा जो sequence आहे सिंगल म्हणजे just constant sequence 2 is bounded. So you should know what is meant by sequence, then what is meant by sequence range set of the sequence, and by considering cardinality of the range set of the sequence you can tell whether the set is bounded or not. कुठलाही set जर तो finite असेल तर तो कायम bounded असतो. We should always know this. Every finite set is bounded, but that doesn't mean every infinite set is not bounded. नेहमी आपण याच्यामध्ये गोंधळ घालतो. Finite set is bounded, that is obvious, but that doesn't mean when the set is not finite it is not bounded, right? Here also, now see this set 1 1 up 1 by 3 1 by n and so on. This is not finite. Ha finite आहे का? नाही, because n will change each time. You are going to get different term, so it is not at all bounded. Sorry, it is not at all finite. It is infinite set, but still it is bounded. Why? Because every element of this set is less than or equal to 1 and greater than or equal to 0. So 0 and 1 are the bounds of this sequence. 0 is lower bound, 1 is upper bound. So set is bounded, but set is infinite. त्यामुळे ह्या गोष्टींमध्ये नेहमी आपण गोंधळ घालतो जर आपलं चांगलं अंडरस्टँडिंग नसेल तर. Finite sets are bounded, obviously, but that never means we are never. Mathematics is a precise science. When you say finite set is bounded, that much only we are saying. We are not claiming that infinite sets are not bounded. Finite च्या विरुद्ध infinite, bounded च्या विरुद्ध not bounded. But it is not so. We have to be very careful about mathematical arguments that we make. When you know that finite set is bounded, that never means infinite set is not bounded. Here infinite set आहे परंतु तो bounded आहे. लक्षात घ्या. परंतु हा infinite set bounded नाहीये, कारण या टर्म्स वाढत जाणार. कंटिन्युअसली द टर्म्स गो ऑन इन्क्रीजिंग. दिस इज इन्क्रीजिंग सिक्वेन्स. दिस इज डिक्रीजिंग सिक्वेन्स ऑफ पॉझिटिव्ह रिअल नंबर्स. आणि त्याच्यामुळे 0 इज द स्मॉलेस्ट. 0 हा काही पॉझिटिव्ह नाही आहे, पण कुठलाही पॉझिटिव्ह रिअल नंबर हा 0 पेक्षा मोठा आहे, म्हणून 0 हा त्याचा लोअर बाउंड झाला या सिक्वेन्सचा. आणि 1 हा अपर बाउंड आहे. कुठलाही डिक्रीजिंग सेट तुम्ही ज्यावेळी घेता त्यावेळी पहिली टर्म हा त्याचा अपर बाउंड असतो. सो दिस इज व्हॉट वी हॅव टू अंडरस्टँड. त्यामुळे या लेक्चरमध्ये आपण सिक्वेन्स म्हणजे काय, त्याचा रेंज सेट म्हणजे काय, आणि सिक्वेन्स बाउंडेड असतो म्हणजे काय आणि नॉट बाउंडेड म्हणजे काय, एवढ्या गोष्टी आपण डिस्कस केल्या. ओके, ह्याच्यामधलं हे जे सेकंड एक्झाम्पल आहे, इट इज अनबाउंडेड सिक्वेन्स बट ऑल अदर्स आर बाउंडेड. बरं, हा फायनाईट नाही आहे तरीही तो बाउंडेड आहे, म्हणून इन्फिनाईट सेट्स आर नॉट बाउंडेड हा कन्सेप्ट डोक्यातून काढून टाका. इन्फिनाईट सेट्स क्लोज्ड इंटरवल 0 1 आहे ना. क्लोज्ड इंटरवल 0 1 इन्फायनाइट सेट आहे. देर आर हाऊ मेनी एलिमेंट्स आर देअर बिटवीन 0 and 1? Infinitely many real numbers are there. So it is an infinite set, but it is bounded because 0 is its lower bound, 1 is its upper bound. Okay, so this lecture is devoted only for telling you what is meant by sequence is bounded, how you will check whether sequence is bounded. The rule is write down the range set of the sequence. and if the range set is bounded, sequence is bounded. And also always you know that set which is finite is always bounded. Okay, so I hope you understood whatever is discussed about sequences in this lecture. In the next lecture we will continue about sequences again. Okay, thank you.